Hello everyone. In this episode, I want to talk about the cycles. The cycles are actually the special type of permutations. As we discussed before, permutations are the bijections from a set to itself. So cycles are some special permutations or some special bijections from a set to itself. So let's look at the definition here. It says that a cycle is a string of integers which represents the element of Sn. Sn is the symmetric group of order n as we defined in the previous episode. So it means a cycle is an element of the symmetric group. So because the elements of symmetric group are the permutations, so a cycle is actually a permutation, and this permutation has the special property that it cyclically permutes those integers, and those integers means the integers in the string or integer which represents this cycle, and then it fixes all other integers which is not in this string. Okay, let's look at an example. So let's consider the symmetric group of order of degree 7 when n equals to 7. So we are talking about S7, and this applies for any other integers. You can think about S10, S11, S100. That's the same. We just use 7 as an example here. And according to the definition, S7 is a symmetric group over a set A. A is a set of 7 elements, so that the permutations in S7 are the permutations over the set of 7 elements, which is a set A. And because no matter what set we are considering, as long as it has 7 elements, the permutation are the same, and the elements in the set doesn't matter. So here we can just consider the set of 7 integers, and here we can use the set contains the integers from 1 to 7. So 1, 2, 3, and until 7. Those 7 integers, and the permutations are the permutations over those 7 integers. And then we can think about the cycles now. And let's look at the first example of cycle. We can think about a cycle like this: 2, 5, 3. This is the string of integers as same as we saw in the definition, and those integers are from this set A. So we cannot have like 8 or 10 in this string, because 8 and 10 is not in this set A. Okay, and also we should be careful to leave a space between those integers to so that you can see those integers clearly. And then this string is closed with a round round bracket. And as we saw in the definition, this is a permutation in S7, and we can call it sigma 1. And according to the definition, it should have a special property that it cyclically permute the integers in this string. So the way it permutes those integers is like this. When you permute one integer in this string, the result will be the next integer in this string. which means if you apply this cycle to the first integer 2 in this string, you will get the next one, which is 5. So 2 goes to 5, and similarly, if you apply this cycle to the second integer, which is 5, you get the third one, which is 3 here. And then you can apply this cycle to the integer 3 in this string, because 3 is the last integer in this string, so we cannot go to the next one because there's no next integer. But in the for the last integer, we just go back to the first integer, so it will go back to 2. So this is how this cycle cyclically permutes those integers, because you will get, like, if you start from any integer, maybe you don't start from the first integer 2 here, you start from 5 here, like here. Then you apply the sigma, the cycle on this integer, and you get, as we saw, you get 3, and you apply the cycle to the result 3, and then, as we saw here, you get a 2. Then you apply sigma to 2, you get 5. And here 5 is the same as the first one, so actually you can think about the 2 go back to 5 here. So you will get a diagram like this if you apply the cycle to those integers, and it's actually a circle. You can just it is a circle, and that means the permutation just permute those integers cyclically. Okay, and then we can also look at another example. Maybe sigma 2 equals to 3, 1, and this we're still in the S7 symmetric group. And similarly, if we apply the sigma 2 to 3, we get 1, and 1 because 1 is the last integer in this string, so we go back to the first one, so 1 go back to 3. So this is also a cycle. Okay, then we can define what is the length of a cycle. So this is the definition that says the length of a cycle is the number of integers which appears in it. So it means that, for example, for the cycle we talked about before, this cycle, because it has 3 integers in this string, so it means that it has length 3. And also for this one, 3, 1, it has length 2, because there are only 2 integers. And then we can say that a cycle of length t is called a t-cycle. So it means that for this first cycle, it is of length 3, so it is called 3-cycle. And for this one, it is of length 2, so it is called 2-cycle. So this is the definition of the length of cycles. Okay, then we can think about the meaning of disjoint for cycles. So the definition says that 2 cycles are called disjoint if they have no numbers in common. For example, let's consider the cycles like this 1, 2, 3, and 4, 7. Maybe those two cycles are like also in S7. They are disjoint because they don't have common integers inside their strings. So those two are disjoint. But if we consider 2, 5, 3 and 3, 1, those two we talked about it before. Those two in S7, they are not disjoint. Why? That is because both of them have 3 in common, so those cycles are not disjoint. And why do we care about the disjoint cycles? That is because if we have 2 cycles are disjoint, then they can be commuted. For example, for this one, if we denote sigma 1 is this first cycle and the second cycle is sigma 2, then we will get sigma 1 times sigma 2 equals to sigma 2 times equals sigma 1. And because cycles are permutations and the permutations are bijections, so here the multiplication are actually the composition of the maps. Okay, so we can check that this is true. For example, if we apply sigma 1, sigma 2 on maybe 3, what we get is we apply sigma 2 at first, because here we don't have 3 in this string, so according to the definition of cycle, it will fix 3, so we will get this is 3. We get only sigma 1 apply for 3, and here sigma 1 apply to 3, because 3 is the last integer. We go back to the first one, so we get 1 here. And then sigma 2, sigma 1, and like input 3, we get, because we apply sigma 1 at first, and we input 3, we get 1, so we get this 1 like this, and then apply sigma 2 to the result 1, because 1 is not in this sigma 2, so it fixes this 1, so we get 1. So those are equal to each other. But for the cycles are not disjoint, it will be this will not be true, because let me see. Let's denote this by sigma 3, this first cycle, and this by sigma 4. Then sigma 3, sigma 4 apply to 3, we get sigma 4 applied to 3 is we get 1. So 3, 1, and the 1 is not here, so we get it fixed 1. And then if we consider sigma 4, sigma 3 apply to 3, the same integer 3, then we get sigma 4, and the result of this part is, because 3 here we go to 2, so we get 2. And for sigma 4, because 2 is not in this string, so we fix it 2, and we can see those two are not equal to each other. So this means like those two those two cycles are not commute. Okay, and furthermore, the disjoint cycles are useful to represent the permutation, which we will talk about in the next episode, to use the cycles to denote any permutation in a symmetric group. Okay, see you in the next video. Bye.